Hi, my name is Rohan, and this is the counting circuit. The counting circuit counts from 0 to 9 in decimal, with its direction depending on the state of the slide switch. On top is my finished PCB version, and on the bottom is the breadboard prototype. Here's a list of the parts used in the counting circuit. To start off, here's a greatly simplified version. When the button is pressed, a capacitor is charged, which signals a NAND gate oscillator to begin oscillating. It oscillates at a frequency of about 7 Hz or cycles per second. This clock signal is then fed into a decade counter chip, which counts from 0 to 9. One of the output pins divides the frequency of the clock signal by 10. This is the only pin used. The output of the decade counter is then fed into a binary counter. The binary counter counts from 0 to 9 in binary, advancing the count on each rising edge of the clock signal. The 4 outputs from the 0 to 9 binary counter are then fed into one final chip, a binary decimal decoder. This chip converts the binary number to a signal readable by a 7-segment display. The 7-segment display displays the number. Here's a breakdown of how each section performs its function, starting with the NAND gate oscillator. The NAND gate oscillator is controlled by two resistor-capacitor pairs, the first of which, RC1, controls the duration of the clock signal provided. When the button is pressed, C1 is charged up instantly, as there is no series resistor. C1 slowly drains through R2. When RC1 is charged, a high signal on NG2 goes through R4, and fills up C2 until the resistance is more than 470 ohms. The signal then feeds back on itself into NG2's input. If RC1 remains charged, NG2 receives two high signals and outputs a low. This causes C2 to drain and NG3 to output a high signal. NG4 acts as a NOT gate, so it outputs a low signal. When the capacitor no longer provides half the input voltage, one of the inputs of NG2 registers a low signal and outputs high again. This process repeats constantly until C1 drains below 4.5 volts, flashing the LED as shown. The clock signal output of the NAND gate oscillator is fed into the decade counter, IC. When the pins are properly conditioned, reset and enable are both on low, the decade counter repeatedly counts from 0 to 9 on the rising edge of the clock pulse, as long as the NAND gate oscillator provides the clock signal. The result, when connected to an LED bar, is shown. The decade counter serves one additional purpose. The divide 10 pin is high for the counts 0 to 4 and low for counts 5 to 9. This effectively causes the pin to divide the clock signal frequency by 10. This function is useful in the case of the counting circuit to reduce the rate of counting enough to properly observe the changes. The divide 10 output of the decade counter is connected to the clock input of the BCD counter. Just like the decade counter, the BCD counter counts repeatedly from 0 to 9 on the rising edge of the clock signal. Unlike the decade counter, however, the BCD counter counts in binary. It has 4 outputs. Each represents a binary digit, with high representing 1 and low representing 0. Shown is the result with the new divided clock signal output from the decade counter. The BCD counter can also count in either direction. This function is set with the up/down pin. When low, it counts down. When high, it counts up. The 4 outputs of the BCD counter are fed into a BCD decoder. This decoder chip converts the binary number to the correct decimal number on the 7-segment display. It does this with a complex arrangement of logic gates embedded inside. The result is a circuit that counts from 0 to 9 on a 7-segment display. This is how the breadboard prototype works. Here is a permanent PCB version in a 3D printed case. Just like the breadboard, the PCB has the capability to count both up and down. Finally, here is a dual-digit counting circuit. It counts from 0 to 99. It works very similarly to the single-digit counting circuit with a few minor modifications. Firstly, a larger capacitor has been put in to the NGO to allow for extended counting. Most notably, the dual-digit counting circuit contains a second BCD counter with its clock input driven by the carryout pin of the first counter. This signal completes a cycle every time the count reaches 0, or 9 when counting down. Just like the single-digit counting circuit, the dual-digit counting circuit can count both up and down. Thank you for watching until the end. Hopefully this video provided some valuable insight into how the counting circuit works.